Okay, so like I said, we're going to go over two methods, time series optimization and the characteristic nonlinear system identification. The time series one is just for you to have just to know about it, and then you'll actually have an assignment on the characteristic. We already do have an assignment on that, on the characteristic nonlinear system ID. So the basic concept with time series optimization is it's a parametric method that identifies parameter values simply by maximizing the fit between a simulation result and a measurement. And so this is a very brute force way of finding your way into some model that reproduces that response. You typically need to know something about the physics to do this because you have to select a model a priori before running this kind of optimization. And it really only works well for simulations that are cheap to run, computationally cheap. So only like a few degrees of freedom or discrete systems. Something like, for example, a model airplane that you can reduce down in finite elements down to like 130 degrees of freedom would not work well for this. Just because you have to directly simulate it, and that takes a lot of time for larger models. And if you're thinking something like a high fidelity finite element model, then this would never work because it would just take way too long. And that reason for that is when we're doing these optimization routines, we're looking on the order of hundreds of thousands to millions of function evaluations or simulations in order to optimize this. So like I said, it's very brute force. Very brute force, but it works well when you know the physics and you only have a few degrees of freedom. All right, so the basic idea is that we're going to try and define some objective function that ultimately will maximize the fit between the simulated response and a measured response. And then you're generally going to want to use a global optimization technique for this. You can use many different kinds of metrics. What I have used most often and found to work quite well is just the plain old R squared that you learned in like intro statistics. With that in mind, we're going to take a look and say that XE here is our measured response, E for experiment, and then S is the simulated response, S for simulation, on some time interval from 0 to big T. Then in this case, you can define the R squared metric to be equal to 1 minus the fraction. The numerator, we're going to be summing over time of XE minus XS, that quantity squared. And then we're dividing by the summation over time of the quantity XE minus XE tilde, that quantity squared. And here the tilde means the mean value. And so we are summing the squares of this difference. We're not squaring the summation. We are summing the individual squares. This is your basic R squared metric that you have learned previously. It was designed for linear equations, but it happens to work well in this context as well anyway. In fact, I found that it works well in a lot of contexts where it shouldn't work, or a statistician would probably complain about you applying it. But I don't know, things work, and we're engineers, we're in the job of, finishing things and getting things to work. So if it works, it works. Whether or not that violates the essence of what you're doing, whatever. That's a debate we can have. Okay, so in this case, let's simplify this R squared, and let's call it 1 minus P. And here P will be some function of lambda, and lambda just represents whatever the parameters are in the equation of motion you're trying to model. And then we can write our objective function as we want to minimize the value P for or where here lambda lives in some subset of the real numbers, assuming that you were using real valued equations. And that's an Rn. So generally, we're going to provide some kind of upper and lower bound on the parameters in the system, and those tend to come from experience and just having some idea of what you're doing with the system. Again, this is an approach that works really well when you have insight into the physics already. And so the R squared, just if you're not aware, R squared is some value from minus infinity to 1, 1 being a perfect fit. And so we want the R squared to be as close to 1 as we possibly can get, and that corresponds to having the smallest value of p as we can possibly have, and that's why we're going to try and minimize p. All right, another reason I like r squared is that it's very easy to understand, and everybody has seen it before, so it's easy to talk about with other people, and it has meaning in its value, whereas something like mean square error is going to be different for every different signal you try. So there's not really a way to compare different systems in terms of performance with mean square errors. That's my opinion.
What you're saying, like the r squared method is like normalized?
Yeah, I mean, r squared is a value from minus infinity to 1 for everything you throw into it. And so if you have a good fit in one system, you get a high r squared. And if you have a totally different type of system and you compute an r squared in that, and you get close to 1, you know that's good as well. But the mean square error might be, I don't know, 300,000 for one case, and that's very low, actually. It sounds high, but that could actually be very low for whatever application. And then it's like 100 in another application. And there's not really a way to compare those without kind of understanding what's going into it. But there are many, many different metrics you can use out there. R squared happens to be my particular favorite because I've had a lot of success with it. Okay. So again, we're studying vibration systems, particularly looking at transient response in this kind of method. And what I have found is that the pure optimization function in equation 4, it can tend to be too aggressive in that it will sometimes force a damping to be too strong, and therefore forcing the response to 0 quicker than you see in an actual observation. And so in order to prevent that, we can add some kind of constraints to it. And particularly, we can just say that it needs to stay within some percentage, plus or minus a, of the response amplitude for the last b% of that duration. And I think we might have a plot of that somewhere. No, we don't. But we'll talk about this in a moment. So by adding those constraints, we can say that we want to minimize p, which is still dependent on all the parameters lambda, subject to the constraints that the maximum value of the simulated signal for tau must be greater or equal to 1 minus a times the maximum of the absolute of xe for tau. And we'll say what tau is in a moment. That's our first constraint. We'll write out the second one, and then we'll talk about these separately. The second constraint we can say is that we want the maximum value of xs for tau to be less than or equal to, in this case, 1 plus a times the maximum value, the absolute value of xe for tau, where, so lambda still lives in U, which is that subset of the real numbers, assuming you have some upper and lower bounds on it, and tau here lives in the interval of 1 minus b times big T up to t. So if b is 0.2, tau is from 80% of the duration to the full duration, so the last 20% of the signal, where we would expect it to have the lowest amplitude due to just damping out in a transient response. Okay, so that first constraint says that, let's just give a number. If a is 0.3, then the maximum value of our simulated signal needs to be at least equal to 70% of the maximum value of the experimental signal in that last 20% or b% of the response. And then the second constraint says that it cannot exceed a, or we said a was 0.3 or 30%, so it cannot exceed 30% of that maximum amplitude. And so this is just a way to constrain the optimization to not make the damping too aggressive. Okay, you guys won't really need to do this in your homework, but if you ever have a system where you know the behavior, you've designed it based on some underlying physics that you understand, you can apply this. So I'm going to show an example here for the LO-NO system that we've seen several different times throughout this course. In this case, this is the experimental version of that structure. On the left of that picture is just the CAD model of it. On the right is the actual experimental system. I'm going to try to zoom in here and see if I can point something out. So I'm just going to draw right here and right here, which is hard to see, but if you read the paper, there's probably a better view. There's small steel wires that run underneath the NO here, and those steel wires couple the NO to the LO and introduce a strong, smooth nonlinearity. All right, and the reference is given there. We also have a pair of thin, these guys right here, thin steel flexures that add a linear stiffness to this model. All right, we're assuming the nonlinearity to be smooth, and then we're going to model it using a generic polynomial. That generic polynomial is right here, and there's also a linear coupling term right here, and then a linear coupling damping term. What else can I say? All right, so we measured the mass of both of these degrees of freedom, something that can be done rather easily. We then did, before we installed the NO, we actually did a linear identification of the LO and identified the following parameters. We found that the linear damping for the LO was 2.177 Newton seconds per meter. That gives the LO a linear damping ratio of 0.00671. And then we found that the grounding stiffness, or K1, this is equal to 19239 newtons per meter. And then the figure shown here is on the left is a comparison of the transient response from the model for the LO and the experimental measurement for only the LO with no NO installed on it. The two wavelet transforms, and to the right is the Fourier spectrum, which is what you would use, what we used, that Fourier spectrum to identify those parameters. And you can see the comparison between the model and the experiment, and in general the agreement is good. Which it should be because it's just a linear harmonic oscillator. Okay. So, given that, what we don't know is the coupling damper, B2, the coupling linear stiffness, the coupling nonlinear stiffness, and the power in the generalized polynomial that we've chosen. So in order to identify those, we're going to employ this time series optimization technique, and the objective function is shown here. We're going to minimize that p-value subject to those two constraints here, that a value is 0.3, and then those are the bounds for every parameter shown there. And in this case, the b value in terms of the last percentage of the response is 0.2, so the last 20%. And the upper and lower bounds for this mostly come from experience with these types of wires and this type of system, this type of nonlinearity. Okay. So shown now is a table which shows the initial guess that we provided for this. Again, this is kind of based on experience as well, but as long as it's within those bounds, you can really give it any initial guess, and the optimization will eventually find the global minimum, provided you control it the right way or give it the right optional variables. And then to the right, you can see our identified values, which are close to what we started with. Again, because of some experience in doing, for example, doing basic hand calculations for the stiffness of those flexures based on beam theory. Or even, in this case, they're cantilever plates, and you can use cantilever plate theory. Okay, so with that model, here is a comparison of on the left is the LO response for the impact that we use to do this identification. One thing I didn't mention is that the impact is actually applied to the NO in this case, so we're hitting the top floor, not the bottom floor. And then to the right is the comparison between the experiment and model for the NO. And again, you can see that we have a good agreement in time series as well as in the wavelet domain and the Fourier domain. Okay. So as always, we want to do a validation with a case that was not used in the identification. And so here is a case where we hit the NO with a force of only 37 newtons, so substantially smaller. And again, you can see that our model does a good job of reproducing the behavior in all three of those domains. And also for a higher force, you can see here, and the model does a good job of matching this. There is some deviation, particularly in the NO response here. Likely due to the fact that we're using linear viscous damping and nothing is linear viscous. And of course, there's friction in the structure that we didn't model and so forth, and jointed mechanics that was not accounted for either. There might be a code for this. I actually did include the code for this approach shown here. So one thing that I'll say about this code is this is the actual experimental data. So you wouldn't be able to just copy this code and run this. You would need the experimental data. But you would want to use your own. What else? First portion on the right is a lot of it is just processing. Then we get down to the initial guesses. The upper and lower bounds, which have all been scaled to go from 0 to 1. All of the options that are used here to force this thing to find a true global minimum. And by the way, when I say this stuff can take long to run this model and optimize it, when we did it took maybe like 12 hours. So I mean, this is a very simple system and we're still waiting 12 hours. That's why I'm saying the cost of this goes way up when you increase degrees of freedom. When you know the physics, it's very useful though, because you can get very accurate results. And that's especially useful when you're trying to confirm theoretical behavior experimentally. Okay.
How can you be sure if you're not stuck in the local minimum?
Sure. So one thing to do, and what we'll typically do, there's a couple things you can do. Generally, you want to choose different initial conditions and test that. Second, let me back up before that. So we're using a method known as pattern search, and this is a global optimization technique. And rather than something like fmin-con or fmin search, which are only local minimizers. So the other thing we do is that we push the tolerance on the function down to machine epsilon. We push the tolerance on x values down to machine epsilon. We force the maximum function evaluations to like 10 billion, as well as the number of iterations to 10 billion. And we force it to go down until it finds that this mesh is as small as it possibly can be. And I'm not sure about this particular system, but I've done this before where it will go down to a mesh size of like 10 to the minus 10, and then actually come back out and go all the way up to a much higher mesh, and then go down, and it will oscillate at times to find better ones. That is why this takes so long to find this true minimum. Without these settings, it doesn't necessarily take that long. That's the price we're paying to really try and force to find as close to a true minimum as we can. So another reason we use pattern search here is because of the constraints that we apply, which I'll point those out here. The constraints are here. The way these have been implemented, the objective function is not smooth. Not to say that it was smooth without these. I don't even think it would be smooth without these, but for sure it's not smooth with these, which means that you can't compute gradients. And that's why we're using pattern search, to do a direct search rather than some gradient descent, because it's not smooth. For sure it's not smooth with these constraints. It's probably not smooth without the constraints, but I don't know. I don't really have a way of knowing that. And you can see that if we violate the constraint, we suddenly set that p-value to 10 to the 15th, so massive. And we're trying to maximize the R squared, so we want p to be extremely small. I think in this particular system, that p-value ends up being something like 0.01, 0.02. The R-squareds are in the high 90s for both the LO and the NAS, and the NO in this case. Okay, you can also see that, I'll add a comment here. This portion right here is for the LO, this one is for the NO. So we're trying to optimize and match the time series of both degrees of freedom simultaneously. And here they're weighted the same, but you could change the scaling of one of these to weight one more than the other. So I've only ever used this technique when I know what the equation is. And I'm just trying to brute force my way to an answer, and I'm willing to wait a day or whatever, however long it takes. All right, any other questions?
So this optimization will return the values for the parameters?
Yeah. Yep, so it won't, well, it's possible that it might return a 0 value, and then you know you can not include that in a model. So when we talk about SIND, we'll talk about dictionaries of terms. So in the model here, we've just assumed that it's this this smooth polynomial type nonlinearity. However, you could make this, you could expand this into many different terms. You could add whatever you want in there, whatever you think belongs in there, and this method will work. Now, of course, the more parameters, the longer it's going to take as well, and the accuracy. Generally, one thing you can do, although you run a risk with this, you can run the optimization without those extreme optional parameters being set, and find a local minimum, and then try turning this on using that local minimum as a initial point. You may or may not be able to find a better point. It depends. Generally, I try different initial conditions and kind of see what happens. And another thing I do is once, even applying these extreme constraints, once it's converged, I then toss those initial conditions back into it. The ones that it found, and I'll toss those back in and make sure that it truly converged.
So how much longer does adding like 1 degree of freedom make this take?
Oh, I don't know. This is you use it when you need it kind of technique, not one that is like widely studied and been classified.
So you said you just modeled the connections between the NO and the LO as just rigid connections, correct?
No, they're modeled with the polynomial stiffness, nonlinearity.
Well, I mean, so you didn't model any like stiffness or damping at the joint, the bolted joint, right?
So, yeah, we modeled this system as follows. So we assume that the LO is grounded and only has a linear spring and a linear damper. That's our LO. For the NO, we assume that there is a linear damper and a nonlinear spring. And all of those terms from the joints, the friction, all of that, we want to lump into these two elements. That nonlinear stiffness term, and which includes a linear stiffness and that linear damper. We're just lumping everything in there. And that's why you can see that we, for the response that we use to identify it, except for maybe at the end, we do a really good job, which you should, because that's what we identified it on.
That's why I was asking.
And then you can see here, it goes out of phase there.
So if you were to add, like throw an extra spring and a damper connect, with a little massless connection between the whatever, how much longer would that just take, like an extra 12 hours or something?
I mean, it depends on what kind of model you're using and the dynamics of it. But I mean, really, and this is a very low amplitude response, and we're able to capture the majority of the details. What you're asking is, what you're looking to add is small effects,
Right.
which can be computationally extraordinarily expensive. If you wanted to try, let's say we tried to model those joints using an I1 element, I'm not so sure you would be able to do this technique. Certainly, if you wanted to go to the point where you had finite elements in there and you were modeling it that way, this would never work. Again, this is good for simple models. And it's because it's just brute force. You're literally just brute forcing your way into a solution through optimization. And of course, as computers get better, this will become easier. But I mean, until we have like the next revolution in computing, I was reading about light-based transistors. And once we get something like that, we'll get improvements of like thousands of times compared to what we have. Then you might do something like that. But for now, keep it down to simple things.
So when we were talking about knowing the physics of the system,
Yeah.
is that where you were able to define these constraints?
So those constraints,
Because I see that you chose this initial guess somehow.
right.
I'm on the midpoint.
Yeah, so the two constraints at the top, those are just based on the response. The upper and lower bounds, those are, except for the tau, that's again the duration measurement of it. The other ones is based on what you expect, which comes from some physical understanding of these things. So for example, if we come back up here, we did a linear identification for the LO, and we found that B is 2, roughly 2. So given that the NO is installed on the LO in a very similar way, we would not expect its damping to be much different. And in fact, what do we find? We find that it's 1. We'd actually expect it to be less because it's got thinner flexures and less, the flexures have a big hole in them as well. And in this case, the flexures are really the biggest source of that damping. And the wires add some type of friction as well, but that's small. So yeah, it's useful when you have an idea of what you're looking for and you have something to base it on. Now, of course, you can just toss whatever you want in here, and you may not find a unique solution as a risk with this as well, depending on those parameters. Meaning that you can have multiple models that can reproduce the same behavior, and if you're only looking at a particular response, that would be a problem. Again, why you got to do this validation. And it's possible to extend this to simulate multiple different responses as well and try and combine different data sets and different regimes. It all comes down to how long do you want to wait. And you can just run it on a server as well. So like, if you're really worried, then you just put it on a server and let it go. The real caution is don't try to do this when you need like dozens of degrees of freedom. That's where this will not benefit you. Unless you can wait, unless you're willing to wait like 2 months or something, then by all means. And if you've got thousands of degrees of freedom, it'll never work. It'll just never run. Okay, any other questions? All right. In that case, we're going to switch and now talk about the characteristic nonlinear system identification. So this is a technique for identifying the dynamics of what are known as local nonlinear attachments. And we're going to talk about what a local attachment is. And so local attachments are small, low-mass components that are installed in a large primary structure. And when I say small and low mass, that's compared to the primary structure, not compared to like U. For example, I mean, like a 500 kilogram mass is large compared to U, but that's nothing for a skyscraper kind of deal. So it's compared to that primary structure. And some examples are any kind of like rocket or store on a fighter jet wing, even like the fuel pod also. A lot of satellites will have small components, and the famous example is the Cassini spacecraft with this Huygens probe, which exhibited some really interesting nonlinear behavior, and it was actually a local attachment. Its mass should be under 5%, I think, of the whole total spacecraft, maybe less than that. And then we've mentioned nonlinear energy sinks before, and every nonlinear energy sink is a local attachment, falls into this category of local attachments. Okay. All right, so what's interesting about local attachments is that their dynamics can be treated as kind of separate or almost separate from the parent structure. And I'm just going to try and illustrate this using 2 linear examples, and then we'll just kind of wave our hands and pretend that it makes sense for nonlinear systems. But we can easily show how it works for a linear system. So we're just going to start by considering a harmonic oscillator with a local attachment connected to it. The equations are shown there. There's no damping in this particular case because we're just going to study how natural frequencies change as a function of that coupling stiffness. We could put that into matrix form, and then we could compute, using the matrix form, we can compute mode shapes. Oh, whoops. From there, what we're going to do is we are going to change the mass. Okay, so we're going to choose fixed values for the mass of the oscillator and its grounding stiffness. I believe those are provided a little bit lower there. And we're going to vary the mass of the attachment, and then we're going to do a lot of variation on the coupling stiffness, and then we're going to track how the natural frequencies of the system change as a function of that stiffness. And we're going to compare that to the underlying equivalent natural frequency of the local attachment, which is defined as the square root of k sub c over m. So that's the equivalent linear natural frequency of that local attachment if it were its own oscillator grounded. And we're going to compare that to the natural frequencies of the coupled structure. All right, so that's what I'm showing here. This is for the left is for the mass. The local attachment having a mass of 1 really makes it not a local attachment because it's so big compared to the main structure. To the right is 0.5. What I'm showing here, we're going to zoom in on the left plot. So we have two gray lines, dashed one and a dashed dot line. The dashed line at the top there is what you get if you just take the square root of big K over big M. That is the linear, the natural frequency of this primary oscillator without anything installed on it. And then beneath that, in the dashed dot gray line, is the square root of K over the summation of the two oscillator masses. Okay, so what you see here is that at low coupling stiffness, the first mode in Scion, its frequency agrees well with the with omega sub La, which is the linear frequency or equivalent linear frequency of that local attachment. And then as that coupling stiffness increases, eventually that first mode starts to depart from the omega sub La, and then actually ends up converging to that gray dashed dot line. So what's happening here is as that coupling stiffness increases, we can see that this omega sub La is increasing, and then what ends up happening is that the effect of that local attachment is purely to decrease the natural frequency of the first mode, decrease the natural frequency of the primary structure. Okay, so when I've said before that if an NES has a stiffness that makes its local frequency higher than that of a particular mode in a structure, its only effect is to add mass to that mode and decrease its frequency. And that's what we're seeing here. So over here, this is, what did I call them, X and Y. For the mode shape, over here, this mode is going to have a very large response in the oscillator, the primary oscillator, and a very weak response in the attachment. And then over here, we'll have the opposite. We'll have a large amplitude in Y and a small amplitude in X in terms of their mode shapes. Way over here, what you'll find is they actually have, in terms of their amplitudes, an equivalent amplitude. Because they're oscillating as a single body. Okay. If we decrease the mass of the attachment, you'll see that this black dash curve moves a little bit to the left and starts to approach the red curve. And in fact, if we keep decreasing the mass of that local attachment, that black dash curve is going to get closer and closer to this red line until we get to a very low stiffness, and you can see they start to overlap with each other, particularly at a mass of 1%. if we zoom in, you can see what happens here. You can see how in the coupled structure, that first mode in sine is converging to that coupled natural frequency, that gray dashed dot line, while the second mode is diverging away from the original starting stiffness. So the basic idea that we're looking at here is that the change in frequency content here, although the two modes are changing, there's actually a mode switching that occurs somewhere over here, and we'll see this in the next example where I can plot good mode shapes to show you. There's this mode switching that occurs, and over here, actually over here, the motion is isolated to the attachment. Over here, the motion is isolated to the primary oscillator. Over here, the motion becomes isolated to the attachment, and then over here, they become the same. Okay, we're going to take a look at another example, this time using a model airplane wing with a local attachment. We'll eventually come back to this and see how the CNSI is applied to this. For right now, we're just going to consider a linear version of this. And with this, I'll be able to plot the mode shapes, and you'll be able to see how these mode shapes are actually changing as a function of that coupling stiffness. Okay, so this model airplane is shown right there. We modeled it using finite elements, shown here. There's like 36,000 elements or 30,000 elements in there. We used a technique called Craig-Chang reduction to reduce it down to a model with only 36 degrees of freedom. We needed so many in that finite element model to capture joint behaviors, which is not really important, not necessary for in terms of reproducing the dynamics, and that information is also captured in this reduced order model as well. There's a little anchor connected to the wing that our attachment sits on. You can see the anchor is here, attachment here. We've modeled that anchor using that component right there. And in the reduced order model, there's just a little element that sticks out that allows us to attach things to it. Okay. So we're going to do the same thing we just did before. In this case, we have a finite element model for the aircraft, or for this wing. We're going to augment the local attachment to that, and then we're going to change the coupling stiffness and compute the natural frequencies. And we're going to find that there's a similar behavior as what you saw previously, except now it involves many modes, all of the modes of the structure. And I've only plotted the first four of the structure, or only the first four of the structure. Let me go through the gray lines here. So omega sub NA, that means that there's no attachment connected. So that's the natural frequencies of the wing without any attachment installed at all. And then the dashed dot lines at omega sub RA, that is where the attachment is rigid, meaning that we just added that mass to the connection point in the finite element matrices. Rather than attaching it dynamically, it's just adding the mass to that. And so you can see that as the coupling stiffness changes, we go from the frequency where there is no attachment. If I draw quickly, you'll see that this mode goes from the frequency where there is no attachment, then transitions up to the point where there's a rigid attachment, meaning that there's only a mass effect at that point. Okay, so with such a high mass, this attachment is not a local attachment, and that's why this black curve does not really line up with anything. As we decrease the mass, it starts to line up better, and eventually, if you go to a small enough mass, it will eventually converge and lie on top of these as well. Okay, and you can see how it's getting closer and closer to lying on top of those curves as well. Here's a zoomed up view of that. Here's the code that I used to generate all of that. So what I want to show here is we're going to look at three points on this. One like right before this transition regime, one right in the transition regime for that first and second modes, and then one after the first transition regime. And plotted beneath that is the corresponding mode shapes of this system. So at point I, we can see that in mode 1, there's only motion in that local attachment. That's that red circle is that local attachment. There in mode 2, there is actually only motion in the wing. The local attachment has an amplitude of near 0 in this. I'm not sure how much you can see up there. I've also included in light gray the 0 position for the wing and the attachment. So mode 3 is a torsional mode, and again here the attachment has a near zero amplitude, and then mode 4 is a second bending mode. If we go to the second point here, we'll see that there's now some mixing that occurs between the first and the second modes in this transition regime. Whereas mode 3 and mode 4 are not affected by this. And then after we go through that transition regime, you'll see here that the first mode is now a first bending mode with some motion in the local attachment, and that second mode is now almost no motion in the wing and a lot of motion in the attachment. So there's this mode switching that occurs based on that coupling stiffness. Okay. Are there any questions?
Can this process used to be as a design process?
Yeah, you could, of course, for a linear system. But the point I want to make here is that we've been looking at linear coupling stiffness, and you can think of nonlinear stiffness as being like a hardening type nonlinearity. You can think of that as also being a changing in this coupling stiffness, such that if we are considering an oscillator that sits somewhere down here with a high enough nonlinear hardening stiffness, eventually with the right enough energy, its magnitude is going to be here. And so by tracking these changes, we should then be able to, in a sense, identify a model for that. That's the whole idea. Any other questions? All right, so the code that I used to plot these mode shapes is shown there. And then we're going to continue on to our discussion of the CNSI method. So the basic idea is that the CNSI will exploit the localness of this attachment, which in a sense allows us to separate the dynamics from the parent structure and then use that as a way to do some type of data-driven, non-parametric system identification. So the original citation is shown here. The homework problem you have on this topic is in this paper, so when you're working on it, you might want to read through and reference that. I'm not going to show that example. It's in the paper. You can read it. I'll show other examples. What we're going to do is we're going to go through the assumptions, and then we're going to talk about the application of it, and then we'll go through 3 different examples. Okay, so first, the CNSI makes the following assumptions. First, that you know the mass of the attachment is known. Which is something you should be able to measure. Second, that free response measurements for the attachment and its installation points are available. Meaning that you've done some kind of transient vibration measurement and you've measured the response of both the attachment and its anchor points. These are the 2 most critical assumptions, that you know the mass and that you have vibration measurements, transient response measurements. And then there's a third assumption, which is kind of just baked along into all of this anyway. It's that the analyst has basic knowledge of the frequency content of the primary structure. It means that before you install the attachment, you have either done some type of linear finite element modeling, or you've done some linear testing on the structure, which is a very basic step in towards this anyway. This is a thing that if you were really doing this in practice, you would have already done this anyway. So this is not something that is out of the ordinary or not. And then generally when people are doing testing, they've already had a finite element model and they've been studying that for months. And so they have some idea of where the frequencies will lie anyway. And you need to know the basic like frequencies of your primary structure so that you can separate those out from what the local attachment is introducing. So you can tell what component is what. Okay, so the CNSI method has two phases. The first phase is a data processing phase. Where we will analyze the measured responses and extract out information that we can then use to propose the model or select a model and then identify a model as well. And then the second phase is model selection and parameter identification, which we'll just abbreviate that as just model identification. So you'll use the information you gain in phase 1 to propose a model in phase 2, and then also do the identification for that model as well. Okay, so we're going to go through phase 1, then we'll go through phase 2, then we'll look at some examples. So the focus of phase 1 is to create what we call a frequency displacement plot, which is similar to a frequency energy plot, except now we're going to use displacements, and then also come up with an instantaneous damping or instantaneous damping curve. And so the idea is that the FDP will characterize or contain the information needed to characterize the stiffness behavior, and the damping curve will tell us what the damping is doing and allow us to model that. So the first step is to calculate what we call characteristic displacement and characteristic velocity for a particular response. We can abbreviate these as characteristic motion. So when I say characteristic motions, I mean displacement and velocity. And so just to give you a definition up front, the characteristic motions are representations of their corresponding instantaneous amplitudes of the relative motions. And so to this end, let's consider just a generic local attachment. So here we have the schematic showing the attachment. The anchor point is just the response where that attachment is connected to the primary structure, and we are not concerned with what the rest of the structure is doing. We only care about the motion at that attachment point. That structure could be very complicated. It could be a very simple structure. We don't care. We only care about knowing what its motion is at the attachment point and the motion of the attachment itself. We're considering just a generic coupling between the system, and the key thing here is that this delta parameter or delta variable is the relative displacement between the attachment and the anchor as shown up there, and then delta dot is the relative velocity. Okay, so with that in mind, we're going to define the characteristic displacement at a particular time, big T, as being delta sub C over bar if at T is equal to the maximum value of that relative displacement, or maximum value of the absolute value of the relative displacement evaluated for tau, where for all tau within the interval big T up to big T plus delta big T. So we're looking at some window of our signal and choosing the maximum displacement in that window and assigning that to the value, to the time big T. And so delta T here is the period of the lowest participating frequency in the measurement, meaning we're capturing at least one cycle. Okay, so this definition is applicable for both continuous and discrete signals, but we're going to focus on discrete signals. which then means that we can compute the characteristic displacement at the next point in time by shifting our window over by a value of small delta t, which is the sampling period of the measurement. All right, so given that, we can also now define the characteristic velocity, which is exactly the same as equation 13, except instead of using delta, we're going to use delta dot. So we're just going to compute the same thing using the relative velocity. So when we do this, what we end up with is basically a stepping representation of the amplitude of that relative displacement. All right, so here are two examples, which I'm going to zoom in a moment, and hopefully you'll be able to see. I'll zoom in on the velocity. It looks easier to see there. So on the top is relative displacement. Beneath that is relative velocity in black. And then on top of that, we're showing in red the characteristic velocity and displacement as we just defined it, which results in a non-smooth response, which hopefully you can see how the red curve is this kind of stepped response. And in order to smooth that out, we apply a low-pass filter, just using a Butterworth filter. And then when we do that, we remove the overbar from the delta C and the VC. And so that, if I zoom back in here, that sine curve is now the smooth representation of that. Okay, so now that we have characteristic motions, what we can then do is construct a frequency displacement plot simply by plotting the wavelet transform as a function of that characteristic displacement. And I have an example shown here where in that shaded background, that is the wavelet transform plot as a function of the characteristic displacement. And then we can compute an instantaneous frequency by tracking the maximum amplitude of the wavelet transform within a particular frequency range. And so you would define that frequency range based on knowledge of the frequencies of the structure and knowledge of what you think your local attachment is doing. And then we also apply the same smoothing filter here as well. All right. Okay. Then the instantaneous damping curve is going to be defined as follows. In this case, we're going to call this zeta sub c function of time. This is equal to minus delta c dot divided by delta c minus omega c dot over 2 omega c. And so delta c dot here is the time derivative of the characteristic displacement, which is not equal to the characteristic velocity. And then omega sub c is 2 pi times the characteristic frequency. And then omega c dot is just its time derivative. So this formula comes from Feldman, which you have the reference below, beneath this plot. It's in chapter 9, somewhere around there. If you read the paper that I showed in the beginning of this section, you'll find that reference. I actually quote a section from him. And this method is also similar to one by Krylov and Boglibov, which is also cited there as well. Okay, so now that we have the instantaneous frequency as a function of characteristic displacement and the instantaneous damping as a function of the characteristic velocity, or it could be a function of the characteristic displacement as well, we're now ready to go on to phase 2, which is where we're going to do a model selection and a parameter identification. So, like I said, the focus of this phase is to select and then identify a model based on what you found in the previous phase. Meaning that you're going to look at how the instantaneous frequency changes, and then based on that, propose a model for that. And same with the damping. All right, so we're going to consider just a generic attachment with the following equation. We'll say m times y double dot plus b times delta dot plus h hat of delta dot plus k times delta plus g hat of delta, again, and this is all equal to 0. We're going to proceed then by dividing by m, and we're going to rearrange terms to put it into the following form, where we'll have y double dot plus 1 divided by m times the quantity b plus h of delta dot, all of that multiplied by delta dot. So we pulled the delta dot out of h hat, plus 1 over m times the quantity k plus g of delta, all of that multiplied by delta. So again, we pulled the delta out of g, and that's all equal to 0. Okay, based on that, we're going to define the nonlinear frequency of the attachment to be as follows. We'll have capital omega squared, which is now a function of delta, is equal to 1 over m times k plus g of delta. And then the nonlinear damping ratio we're going to define to be zeta of delta dot is equal to 1 over 2m times b plus h delta dot All right, so the nonlinear frequency and nonlinear damping are dependent on the delta and delta dot, which are oscillatory signals, and what we want to do is exchange those for the characteristic motions so that we end up with something that is not oscillating. And to do this, we're going to make the following substitutions. We're going to say that delta, we're going to replace that with 0.85 times delta c. And delta dot, we're going to replace that with 0.85 times vc, or the characteristic velocity. So that 8.85 is not exactly well understood, but there's some theoretical hintings that it's related to harmonic balance techniques and extracting out backbone branches for these kinds of systems. But it's not fully explained, it just works. So after doing that substitution, we can then define the characteristic displacement dependent frequency as the quantity 1 over 2 pi times the square root of 1 over m times k plus g evaluated at 0.85 times delta c. And the damping then becomes 1 over 2m times b plus h evaluated at 0.85 vc. Okay, so at this point, we have created both these equations, and we can just do a curve fitting procedure between the instantaneous frequency we obtained in phase 1 and the instantaneous damping from phase 1 as well. And then from that, we can just directly identify the parameters. So once you get to this point, you've done all of the heavy lifting, and you're now at the point where you can fit a model and then start validating that model. Okay, so we're going to go through some examples. The first is actually just a Duffing oscillator. It turns out that this approach works well for single degree freedoms as well, because the whole basic idea is that when something is a local attachment, you can effectively treat it as a single degree freedom oscillator with a special displacement of delta rather than its own displacement. That's the whole underlying idea. So we're just going to demonstrate this with a Duffing oscillator. In this case, we're just going to use a cubic stiffness nonlinearity and a linear damping. Parameters are shown there. For a Duffing oscillator, the mass doesn't matter because it's only 1 degree freedom, but in this case, it's still kind of small. I simulated the response for And initial condition, this should actually be 10 meters per second.
Is beta omitted for,
Yeah.
Oh yeah, sorry. There's no beta. Yeah, I originally had this not be cubic, but then I decided to make it cubic, just because it's simpler. And in the model, we'll introduce another beta, because we're not going to assume cubic in the model. All right, we're going to simulate for initial velocity of 10 meters per second for up to 2 seconds with sampling rate of 1,000 hertz. We're then going to apply the CNSI method to that. So here's the velocity and displacement response. You can see that there is a very large change in frequency in a very short amount of time, shown here. You can see that in both the wavelet transform as well as in the Fourier transform. There are higher harmonics that occur that are just not shown here. We're interested in that primary component. All right, the code for that is shown right there. Here's what we do in phase one. We first compute the characteristic motions, both the displacement and the velocity. If we zoom on in here, you'll see how that characteristic displacement in red is kind of like stepping function, and we're just smoothing that out. By smoothing it out, we will end up not necessarily capturing everything. And here it looks really close to the amplitude, but there are cases where it's not the instantaneous amplitude. It's a representation of that. We'll see one of those cases later. Okay, so after that, we then move on and plot the wavelet transform as a function of the characteristic displacement shown here, and then we extract out the instantaneous frequency by tracking the maximum amplitude and how that changes in the wavelet transform. So we're tracking the location of that maximum amplitude in the wavelet transform and with respect to that frequency. And that's what that red curve is, and again, this has also been filtered to smooth it out a bit. And the characteristic damping curve, or instantaneous damping, is just calculated using that equation that I gave you. And the code is shown to the right. You can see the zeta term is right here. That's for computing the instantaneous damping, which is relatively flat because it's just a linear viscous system. Okay, so after phase one, we can switch over to phase two. In this case, we're going to model this as a generic polynomial nonlinearity. We're going to say that we have some linear stiffness k sub m times x plus some nonlinear coefficient alpha sub m times x times the absolute value of x raised to the beta sub m. So again, this is just a generic polynomial where beta does not have to be an integer, which gives us some flexibility in capturing this behavior rather than asserting that it's an integer. And I mean, in this case, this instantaneous damping curve is really flat. We have some end effects going on, but in general, it's flat. And with that in mind, we were just going to use a linear viscous damper. In your homework, that particular system has friction in it, and you will need to incorporate dynamic friction in your damping model. Well, you don't necessarily need to, but I had to when I modeled it. And the instantaneous damping curve is representative of something that has friction damping and Coulomb friction damping. Okay, so with that, we can define the characteristic displacement dependent frequency to be 1 over 2 pi times the square root of 1 over m times k sub m plus alpha sub m times xc, and it should be 0.85 times xc. xc here is characteristic displacement. I didn't use delta because there's no relative displacement here. It's just the actual displacement, and that raised to beta sub m. Another thing I'll say is that the characteristic displacement is always going to be positive, so we can get rid of absolute values because it's the same value either way.
When you say dynamic friction, are you talking about like some signum function times x? Okay.
Yep. Yeah, and I believe we talked about that sometime we've talked about that.
Okay.
But like I said, you can read the paper and you'll see what I'm talking about. Okay, so now that we have these two equations, we can directly do a curve fitting procedure and identify the parameters, which is what I did here. For the damping, I neglected, it's very flat in the center, so I actually just neglected these and this region here, and then just computed the mean of that flat portion. For the frequency, I actually did a global optimization using pattern search, which you'll see in the next page. You can see here that the linear stiffness, so I'll add these here. So K, the linear stiffness is actually 300. The actual alpha here is, I think it's 2. Check. It's 3 times 10 to the 8th. The actual beta should have been equal to 2, and the actual B was equal to 0.5. So in general, we're close. The alpha is in the same, at least in the same order, and that beta is reasonably close to 2. We're never going to get like a perfect model out of this. Well, I guess if we asserted that beta was 2 in the model that we proposed for this, we would probably get much closer to the actual alpha value, but real systems are not going to have pure cubic nonlinearities. Okay, so now that we have this model identified, and I didn't calculate it here, but the R squared is going to be like 9999. It's going to be really close. Now that we have that, what we're going to want to do, you can see the code here, you can see I have an objective function, you can see how I did pattern search to fit those curves. This particular optimization runs very fast because it's a very simple optimization. Because the objective function is very fast. There's no simulating anything here. Okay, the last step then is to just validate the response to the model. And in this case, we're only using the case that we used to identify it. Shown here, we just apply the same initial conditions that we did previously, and then we're just plotting and comparing them. And you can see here how our model does a reasonably good job of capturing the transition in the frequency domain and the Weyl transform especially, and in the Fourier domain. And it captures at least the amplitude. It doesn't necessarily capture the phase perfectly. And so this is a model that you generally be happy to use in something, even though it doesn't necessarily capture the damping perfectly. It at least captures the change in amplitude. Okay, we're going to go through 2 more examples. The first is we're going to back to this model airplane wing with that local attachment we saw before. In this case, this attachment is made out of that green T-shaped structure. It is connected to the wing using a single thread flexure. You should see a very thin red line in the bottom picture right here. That is a thin steel flexure that acts as a linear coupling. And then we have 2 thicker steel flexures that are then spaced apart from that T-shaped mass. Okay, so you can see the paper that we studied this right there. You can access that. If you have a PDF version, you should be able to open the link. So the gapped flexures introduce a clearance nonlinearity, which is, while the restoring force of such a system is shown right there. Basically what happens is when the attachment or the relative displacement is larger or less than E, we get a sudden change in stiffness. There's a sudden change in stiffness because it's suddenly contacting these outer flexures. All right, so beneath that I have shown here the actual experimental system with a zoomed in view of that attachment shown there. We measured the response of the wing using accelerometers and the response of the attachment using digital image correlation. We did digital image correlation so that we didn't have to put a sensor on the attachment and mess up its dynamics. This is a case where I forget the mass of this, but it's very small. It's less than 1% of the wing, and it's very sensitive to any kind of wires or things on it. Okay, so looking at the displacement response on the right here, we are impacting the wing like right over here, just underneath that attachment, I believe, or we might have actually impacted over here. I forget. You can read the paper for that, but we're hitting somewhere on the wingtip to maximize the amplitude. Okay, so the anchor, looking at this wavelet transform, you can just see a single component. There's not really that much interesting going on. That's the response of the wing. And then beneath that is the wavelet transform of the attachment, which is much more interesting because you can see there's a very clear transition in the frequency content of this system. Okay, let's go to the next page where we're going to do phase one. Shown at the top there are the relative displacement and the relative velocity, and then their corresponding characteristic motions. If I zoom in here, you'll see how this red curve does not touch exactly that relative displacement, and that's why I mean this is a representation of the instantaneous amplitude. It's not exactly the instantaneous amplitude. And the same thing over here, it doesn't touch. The actual instantaneous amplitude would do something like that. So that's why I mean this is a representation of that instantaneous amplitude. It's not the instantaneous amplitude. Okay, so beneath that we're plotting the corresponding frequency displacement plot, and quite interestingly here there's a very precise characteristic displacement where there is a sudden transition between a linear response, that's just straight line on the left, and then a nonlinear transition on the right. That dashed black line corresponds to a characteristic displacement of 1.856 millimeters, which is very close to the design value for this clearance. It's very difficult to measure clearance gaps like this accurately because the flexures are so thin and flexible that by measuring it, you end up pushing the attachment away. So you artificially inflate that measurement. But it's very close to the design one. On the right is the instantaneous damping curve, and what you can see here is that, again, there's a very sudden transition that occurs at a very precise characteristic displacement. That line actually matches exactly the line on the left. And they're independent. The red dashed line was independently selected from this black dashed line on the left. But they happen to correspond to exactly the same value. And then beneath that, we've zoomed in on the instantaneous curve in that small little region, and mostly it's going to be modeled as some kind of viscous contribution. All right. Okay, so we can now move on to phase two, where we're going to start by proposing a model. We're going to propose this model here, where that red spring and damper represents the red flexure. The blue spring and damper represent those gapped flexures of the clearance nonlinearity. This is just a standard model for a clearance nonlinearity. The equation of motion is shown beneath there. You can expand the signum of delta into delta divided by its absolute value, and then you can rearrange and pull out a delta from the bracketed terms. Yep, you can rearrange it as shown right there. We're missing a square bracket though. And then making the substitutions for the characteristic motions, we'll find that f of delta c is equal to 2 pi times the square root of 1 over m times the quantity k plus alpha divided by delta c times the quantity delta c minus e times the Heaviside function of delta c minus e. As we can divide here by that delta c because it's always going to be positive, it's never going to be 0, by definition. And if you are computing delta c for, well, first of all, there's always going to be noise in your measurements, so it's never going to be 0, quite simply. It's always going to be some positive value. Now, for some kind of simulated system with no noise, you could potentially run into the case where it is 0, in which case you would just truncate and not compute the characteristic displacement up to that point. Okay. Lastly, the damping term is going to be 1 over 2m times d plus beta times the Heaviside function of delta c minus e. So one thing to point out is that the 0.85s canceled above, and inside the Heaviside function, the 0.85 doesn't matter because you applied to both the characteristic displacement and to the clearance as well, and then it doesn't matter because just based on how the Heaviside function works. Okay, with this model shown, you can then go and identify the parameters doing a curve fitting. That's what we did here. The damping model is just two linear viscous dampers, so of course you're going to get as best as you can for that model shown there. The parameters shown to the right, and then down here I'll show the model validation. This is the response we used to do the identification. You can see that it does a good job of reproducing the response in both the early nonlinear regime and then also in the later linear regime, and you can see that the frequency content is well captured. In the paper you can find the other comparison cases. All right, we're going to very quickly go through one more example. We're not going to really write anything for this, I'm just going to talk about it. Another example we did was that we had two-story tower with two NESs, one on each floor installed, and we wanted to use a single measurement to identify both of these simultaneously. I'll let you look through this, but here's a zoomed-in view of the two NESs, one on each floor. Here are some displacement responses of them. This is where knowing the frequency content in your structure plays a role in this, knowing what is an NES response and what is a frequency contributed by the main structure. Phase one, we compute characteristic motions. You can see here very clearly how the characteristic displacement, if I zoom on in there, does not capture that instantaneous amplitude, which would do something like, especially here, it would be doing something like this. It's not instantaneous amplitude, it's a representation of that. Okay, you can see the frequency responses. Here's what they look like when we put them in a frequency displacement plot. We do this for both NESs using that same single measurement. There's some details in the paper as to why we excluded a portion versus including everything. The instantaneous damping shown here, we just fit a linear viscous model to it. Equations of motion shown here. We do the same kind of, start with the motion equations, rearrange them, then come up with two frequencies, and then again we just have linear viscous damping here, so it's nothing special there. Identify parameters, and what really matters is can we validate the model. And in this particular picture, they don't look as good, and that's partially because the red line is very thin compared to the black line, and when you actually zoom in, they do a good job of reproducing the response. Not in this particular picture, but when you zoom in on like MATLAB, and you can get a better resolution. One thing I'll say is that our model is able to capture a lot of transitions like this that occur. And especially if you look at the wavelet domain, the model does a really good job there. And that's usually where we try to qualify and quantify whether our model is doing good or not. This is a response where we didn't use for the identification, and then there's one more right here. Again, we didn't use this for the identification.